Welcome back from the break. We've been exploring relationships that we find in both physics and chemistry. We've looked at the directly proportional relationship, and now we're going to take a look at what it means when we say something is inversely proportional, how we can represent that in words, in a graph, and in a table, and compare the two types of relationships. So one of the things that we need to recognize here is that we can represent directly proportional in a shorthand way. So in our previous example of using force and extension, where we found those were directly proportional, we could actually just say force is directly proportional to the extension. So that's a way of representing it. When we do inversely proportional, we're not going to be able to use that notation directly. Inversely proportional in words means that as one variable increases, the other decreases. So as the one goes up, the other goes down. And you know what? That's what a lot of people write in their tests and exams, and they will get no marks for it because they've forgotten the last little bit. The last little bit to the statement is by the same proportion. So as the one increases, the other decreases by the same proportion. Just the same as we said for directly proportional. When the one variable increased, the other one increased by the same proportion. So don't get that mixed up. Please make sure that you understand there are very specific terms here, very specific relationships, because from these relationships and from the graphs, we're going to be able to write equations, and we will do that in a later scenario. So have a look here in terms of the decrease as well. When the one variable decreases, remember when we say decrease, we can either think of that as dividing, or we can think of it as multiplying by a fraction, by 1 over a value. So for example, 1 over 2. It's the same as dividing by 2, it's just multiplying by a half. So as the one decreases, the other will increase. So they're kind of going counter to each other. Very important that you understand this idea and what impact it has on getting data and looking at it carefully. Now I'm going to look at a very simple relationship about gases, and it's one that you would have experienced, even just blowing up a balloon. You'd recognize that, or pushing on a syringe, you'd recognize that as you push hard on a syringe, what happens to the gas? The gas compresses. So the more pressure you exert, force per unit area, you exert on the gas, the smaller the volume. And as you increase the volume, you decrease the force. The volume increases, the less the pressure. So there's all sorts of apparatus we can use to measure this. And it is an experiment that is called Boyles Law, which you may come across it. But I've just taken some data here to look at it. It's not really important to explain it in terms of Boyles Law, but simply to look at the data. And so what is happening to the pressure? The pressure, you'll see, is decreasing. And what is happening to the volume? Well, if we go from 100 to 400, then as we go down, this is increasing. So we've got a decrease over here, but we've got an increase as we go down in the same direction. So let's have a look at what effect that increase and decrease is all about. Is it a proportional increase and decrease? Well, remember what we did previously? We looked at the factor that we can multiply each term by. So I'm going to have a look at this decrease, and I'm going to say, let's divide this by 2. Could also say multiply by a half, but it's a useful one just to look at. And I'm going to say, if I take 1,200 and I divide by 2, I get 600. What has happened to the volume in relation to that? Well, I started with a volume of 100, and I went all the way down the corresponding value got to 200. So that is an increase of twice the amount. As I divided the one by 2, I multiplied the other by 2. Now, let's do exactly the same for a different set of data. And let's see if it works as well. So I'm going to remove my scribblings from there, and let's see if it follows on. I'm going to start with 800. And I'm going to say, let me divide by 2, and that will give me 400. This is a divide by 2, multiply by half. And what has happened? The 150 was in line with the 800, was my starting point. And look over here, the 300 is in line with the 400. So what has the change been? Well, clearly 150 to 300, the factor is multiply by 2. And so you could do that with other values. You could do it with this one. And you could say, from 600 to 300, I've divided by 2. And if you went from 200 to 400, you'd recognize that you've multiplied by 2. So it looks very much like these are directly proportional values. But what does the graph look like? And can we learn anything from the graph? Well, let's have a careful look at the graph. We recognize at this point there's another way to look at these relationships, and I will come back to that. But if we look at the graph and we try and predict, is there a pattern? I'm just highlighting the values. You'll see that the best fit line doesn't really seem to go through all of them, so it doesn't look like it's a linear relationship. It looks more like a curve. And my freehand curve there is not particularly good. But the problem with curves, it's very difficult to see if there is a mathematical relationship. As it happens, there is. And if you think there is a mathematical relationship, then you can go back to the table of values and see if you can work this out. In this case, I'm going to again erase all my working here, and I'm going to say one of the things that a curved graph that kind of looks like that might remind you of something called a hyperbola. A hyperbola, where in maths we write it as the y value times the x value is equal to a constant. In our terminology, you could take the dependent variable or independent variable multiplied by the dependent variable, and you would get a constant. So in this case, you could take all of these values and you could multiply them together, and you would find that you get 1, 2, 0, 0, 0, 0. And whatever one of these values you did, you would get the same constant. That's another way of checking that it is a directly proportional relationship. So looking at how the values change over time, but also by multiplying these together, you'll get a constant every time. And so we're convinced that this is a directly proportional relationship. But you know what? The graph isn't helpful. Because the graph being a curve, it could be a cubic graph, or it could be a parabola or a part of a parabola. We're not sure. So we have a little trick up our sleeve. Because inversely proportional can also be represented in terms of 1 over, or the reciprocal of pressure. So what I've done is I've taken these pressure values and I've said, let me find the reciprocal. Simply taken that number, 1200, and I've said 1 divided by 120, and I've got this fairly small number. And in each case, I've got the small number. What you now see is that the small numbers do increase in size. It went from 4 decimal places to only 3 decimal places. And so the trend is the same. From 100 to 400, that's going in the same direction. But the numbers are difficult to plot. So what physicists do, and chemists do it as well, is they sometimes introduce a factor. And we've multiplied each of the values by 1,000. And so now we can plot those values onto a graph. And look what happens here. How beautiful is it? All of these points are sitting on a straight line. And the key point is it passes through the origin. And so we now can say that the volume is directly proportional to the reciprocal of pressure. That's how we can represent an inversely proportional relationship. And so I want you to understand that when we're dealing with the idea of inversely proportional, the dependent variable, volume, is directly proportional to the reciprocal. That means 1 over pressure. We say that volume versus pressure is a straight line that passes through the origin. And so we have a very clear way of representing this relationship. Now, I want to bring it all together. And just to remind you that when you're looking at data and you're looking at relationships, the first thing to remember is only allow 2 variables to change: the independent and the dependent. Okay, the others need to stay constant, and we've recognized that. To remember that when things are directly proportional, what that means, and as we've shown, what inversely proportional means. Please never say indirectly proportional. It doesn't really exist. What we've got to remember is these are the important terms for physical sciences, both in physics and chemistry. I hope this has helped you to think about relationships differently, and please join me again when we explore them in a little bit more detail. From me, goodbye.